Now go. Okay, so today we're going to talk about concavity. Our goal is to find the intervals of a function, f, that are concave up or concave down. So it's similar to finding the intervals where a function is decreasing or increasing. Also, students will be able to find an inflection point. So it helps if we know what concave up and concave down means before we can find the intervals where a function is concave up or concave down, and what an inflection point means. So if we look at a graph, just a random graph. From science, you probably have heard the word concavity before. So what do we usually mean by concavity or concave?
Like curved.
Curved, inward, forms kind of a cave. So when we consider the pieces of our graph, we would consider this piece here concave down because it's facing down, that piece of graph. Our cave is facing down, and this piece here, concave up. So assuming this point is, we'll say 0.5. That's pretty close to the x-axis, or the y-axis. I just drew a random one. We would say our function is concave down from negative infinity to 0.5, and concave up from 0.5 to infinity. And then we would consider the point where it switches our inflection point. So that's what we mean by an inflection point. So just like when we switch from increasing to decreasing, we had a maximum, or from decreasing to increasing, we had a minimum. If we switch concavity, but this time it doesn't matter which way if we go from concave down to concave up, we still call the point that goes from concave up to concave down an inflection point. It doesn't have a special name when you have one way to the other, whereas max and min does. So an inflection point is just where we switch concavity. If we switch from concave up to concave down, or concave down to concave up, no matter what, we call that point an inflection point. So if f prime told us about increasing or decreasing, which function do you think will tell us about concavity? We're trying to find stuff about f itself, f of x. We know f prime tells us about increasing or decreasing. So what's left to tell us about concavity? F double prime, the next one on the list. So f double prime is what we're going to be focusing on today. So if we look at y equals x cubed, let's draw the graph. Doesn't have to be a particularly fantastic graph, but we know it would look like this. So the concavity is not as apparent here. It's not as distinct as the concavity on the one we drew originally, but it still has concavity, and it still switches concavity. So we're going to let f double prime tell us how it switches concavity. So first we need to find f double prime, or y double prime. So what's y prime? 3x squared y double prime is 6x. If we draw that line in, start at 0, our slope is up 1, 2, 3, 4, 5, 6 over 1, down 1, 2, 3, 4, 5, 6 over 1. So again, we're trying to get the second derivative to tell us information about f of x itself. So being able to see f of x is helpful on this one because we can tell where it's concave down and concave up. I know my graph is concave down from negative infinity to 0, concave up from 0 to infinity. So then we want to look at f double prime and see if there's any distinctive parts about f double prime when we're on that same interval. So if I'm on the interval from negative infinity to 0, how is that different from 0 to infinity when I'm on f double prime? So do we change increasing? Do we change sign? What is different about those two intervals? And how do we change sign on this? We go to from negative to positive. So what kind of concavity did we have on this interval from negative infinity to 0? Concave up or concave down? Concave down. So now we can associate something about this with concave down. So what did we say happened with f double prime on this same interval? Not decreasing, negative. We said this piece is negative. It's increasing overall because when we talk about increasing and decreasing, we always travel from left to right. So left to right, I'm going up. So we can say if y double prime is less than 0, y is concave down. So just like y prime being less than 0 told us something about the original graph, y double prime being negative tells us something about y. So what would happen if we're looking at this other interval? What would our rules say for our other interval? If y double prime is what?
Y double prime is greater than 0, y is
Y double prime is greater than 0, y is concave up. And where is our inflection point on this particular graph? 0. So if y double prime equals 0 and we switch concavity, so we would know we would switch concavity if f double prime goes from positive to negative or negative to positive. Because it's possible to still have a critical point and not switch concavity. I'll show you an example of that in a second. Stop doing that. So if y double prime equals 0 and we switch or does not exist. I always forget that one as well because that doesn't come up as much, but it is a possibility. It's one of those details. So if y double prime equals 0 or does not exist, and we switch concavity, f double prime goes from, oh, that's just to say how we switch concavity, then we have a critical point, or an inflection point. possible to still get that y double prime equaling 0 or not existing, but not be an inflection point, is something like this. This would come up when we tried to set y double prime equal to 0, this x value, we'll call it x equals c. But when we perform our line test, we would get negative to negative. How did I look at that graph and decide that went from negative to negative? If I'm doing a line test for y double prime. So how did I just look at that graph and say, oh, that section would be negative? Because it's concave down. When we were concave down, we said y double prime was negative. They're both concave down, so they're both negative. But C would come up as a point that's a possible inflection point, because if we have a cusp, a pointy part, our derivative wouldn't exist there. So our derivative wouldn't exist for y double prime, so it would come up as one of those points we're supposed to check. So this is just one of the possible situations where our concavity might not actually switch. So let's do an example. I'm going to pause for a second though, because I still see people writing, so I don't want to jump ahead before everyone is done. So let's find the intervals where f of x is concave up and concave down, also named the inflection points. And our function is y equals e to the negative x squared. Now this is almost exactly like first derivative test, except we use the second derivative. So first derivative test can tell us our maxes and mins and where we're increasing or decreasing. This test can tell us concavity, but instead of needing just the first derivative, we need the second derivative. So if y equals e to the negative x squared, what rule am I going to have to use to take the first derivative? Chain rule. Emma was correct, although very quiet. And then after chain rule, when we try and take the second derivative, we're going to have to do product rule and chain rule. So to get some practice taking derivatives, I'm going to have you guys find the first and the second derivative. So we got y prime is e to the negative x squared times negative 2x. And then if you clean up y double prime, you get 4x squared e to the negative 2x minus 2e to the negative, sorry, not to the negative 2x, to the negative x squared, right? Is that what we get when we clean it up?
That's what I got.
Okay.
That's what Josh got.
So now, what do I have to do with this second derivative? Set it equal to 0. See if there's any spots where this would not exist. Now, anytime we have a negative exponent, that could create problems for us for the does not exist. But before we even consider that, I can do some factoring. Usually when we set these equal to 0, our best option is either factor, and if it's not going to factor, then probably we have to use a calculator. But what could I factor out? 2e to the negative x squared. So that would leave us with 2x squared minus 1. So now if I set each piece equal to 0, what do we know about the function e? What do we know about the graph graph of e. If I just have plain old e, it would look something like this. This graph is negative, so it flips horizontally because our negative is on the inside. So this graph would be something like this-ish. But what do we know about that graph? It never equals 0. E will never equal 0, and they like to use that fact quite a bit on the AP test. The E will never equal 0. Unless we had some sort of vertical or horizontal shift. Well, actually, horizontal shift wouldn't do it. If we had some sort of vertical shift down, then we would cross through 0. But as of now, it never equals 0. So this one we don't use. If we considered 2 over e to the x squared in its positive form, so that might cause us problems because we would wonder, well, what if we got 0 in the denominator? But as we just discussed, e to the exponent is never 0, so that one we can throw out as well. Neither of those affected our problem. So then we add 1 to both sides. So again, that fact that e to something is never 0 and never negative is an important fact we need to know. It's used a lot on the AP test. So now we solve this, so we get 2x squared equals 1, x equals, I'm just going to square root of 1/2. But we do have to consider the plus or minus. So we could either leave it as square root of 1/2. They might write it as 1 over square root 2, because square root of 1 is 1, square root 2 we can't take. Or, because it's in the denominator, they may rationalize this radical and say plus or minus square root 2 over 2. If this were a free response, you could really use any of those 3 forms. If it was multiple choice, you just need to be able to recognize any of those 3 forms. And then we do the same thing. We still perform a line test. We need to know information about the second derivative. We need to know where's the second derivative positive and where's the second derivative negative. I don't know why I put 0 in that list because it's not one of our points we're looking at. So if I didn't have a calculator on this question, how would we know what value is smaller than negative square root 2 over 2? We can know, we're pretty sure 0 is between these two because we go from negative to positive. So we can pick that test point pretty easily. But how do I know what to pick over here?
The square root of 2 is still less than 2.
Square root of 2 is less than 2. So
Anything more than 1 or 1.
it can't even be as big as 1 because we have something less than 2 divided by 2. Does that make sense?
Yes.
So we kind of have to think in general terms. So we could use negative 1. I also remember that negative square root of 2 is like 1.414, and then something, something, something. So if I divide that in half, 0.7 is less than 1. And then 1. But what are we going to plug these values into? That's if we have extreme value theorem. That's if we're on a closed interval.
Y double prime.
We plug it into y double prime, just like when we were doing increasing and decreasing, we plugged it into y prime. Because we need to know if y double prime is positive or negative, because that can tell us about y itself. So we plugged these into y double prime, which was something I can't see anymore. And again, we don't really need to worry about this first part because what's going to happen with 2e to the negative x squared every time? It's always positive. E to something is always positive. So this piece here, always positive. 2e to the negative x squared minus 2x squared minus 1. This is always, always positive. So we just need to know about the other half. We don't have to plug these into E itself. We just need to know what happens if I plug in -1. So what happens if I plug in -1?
You can get a positive.
-1 squared is positive, 2 times 1 is positive, minus 1 is positive. So what do we know about y from that positive there? Y is concave down or concave up when it's positive? Concave up. So then we plug in 0. When we plug in 0, we get negative. And when we plug in 1, we get positive. So now I know my intervals are concave up from -infinity to -√2/2 and √2/2 to infinity. Concave down between those two values, between -√2/2 and +√2/2. And where's our inflection point? So we have an inflection point if we did switch concavity. So did we switch concavity from, or at -√2/2? Did our concavity go from up to down or down to up? Thank you. Did we switch sign there? That'll tell us if we switched concavity. Yes. We went from positive to negative. What about at +√2/2? Yes, again, negative to positive. So we have plus or minus √2/2, or you could have listed them separately. Those are both inflection points. It would not have been an inflection point if, say, we had all positive, then we have no inflection points, or concave up, or up everywhere. It would look something like this. Concave up everywhere, we'd have these cusps instead. Or if we even just had positive to positive and then to negative, only √2/2 would be an inflection point. And negative √2/2 wouldn't be one because we went from positive to positive. So, our assignment. Pretty straightforward this time.
Is there any way I can still, are you in the middle of something?
Nope, we're actually just finishing. Let her write down the assignment. No, no, no.
Hey, Linda.
It worked.